I guess I'll at all. And after we do the exercise, I'll do a brief lecture, maybe 5 minutes, 10 minutes. I don't know. We'll see how it goes. And then you'll literally work through 2 programs today. I posted a Word document in the community. Faculty members, if you can go to the community and print out the Word document in the meantime, that will be great. As always, groups of 2 or 3. You will see the programming examples in the Word document. You will literally trace them. Okay, in the process of tracing them, you will understand the algorithm, how these things are done. Okay, very simple task, right? Quick exercise, a little bit of lecture, and then tracing the code. Okay? And then while you're doing all of those things, if you get any questions, your faculty members are there to assist you. If you get stuck in tracing the code, very hard for me to help you online when you're tracing the code. I'll try, but people closest to you should be able to help you easy. Now, more than the faculty members, talk to your other neighbor groups, okay? And see if they can resolve the issue. Of course, you're always welcome to talk to the faculty member there. Okay? Trust me on that. More than faculty members don't take this with any anxiety. Students are smarter than the faculty members, including, I say that to my students here too. Okay? Because they do so much of coding these days, especially in this country. I have my 11th grade daughters who know Java better than I do. Okay, just to give you an example. Okay, so what exercise today is about adjacency matrix. You must be thinking all of a sudden, where did the professor get this exercise from? What has this got to do with data structures class, right? So it turns out we use adjacency matrix quite a lot in computer science as well as in math, like graph theory. Remember when we talked about trees and all that, they are all graphs, right? Graphs without cycles are trees. Implement some of the programs that I will make you trace today. So that's why first I gave you an example. Okay, it's nothing but a connection matrix. Okay, so you have a graph, and graph has what vertices and edges, right? So you can use the concept of a matrix to represent a graph. Okay, so what you're seeing there is a graph which has 4, 1, 1, 2, 3, 4, right? That's a graph. You all agree? Drawn as a tree, but tree is a graph, right? So how do I represent that? Because there is no, see, ultimately, when you draw a tree or something, it's just a representation, right? It's a conceptual model, right? These abstractions, what is abstraction? Abstraction is some kind of a model that will help you visualize the problem that you're trying to solve, okay? But if you go to the programming language, you don't have a syntax called tree. Just like how you declare integer I, you cannot say tree I. Is there any programming language where you can say tree I? Not to my knowledge. Okay. However, we can realize a tree through other concepts, tree or a graph, whatever, right? And one of the nice concepts that we have is a 2-dimensional array. Table is nothing but a 2-dimensional array, right? Matrix is a 2-dimensional array. So we transpose that graph into a matrix. So how do we do that? That's what is explained in the statement above, right? So the rows and columns are labeled by the graph vertices. So this has four vertices. So you see on the top 4 columns, right? Similarly, you have 4 rows. Row 1 corresponds to graph label 1, node label 1, right? Row 2 is is the node label 2, row 3 is the node label 3, and row 4 is the node label 4. Similarly, column 1, 2, 3, 4. Okay. Column 1 represents node 1, column 2 represents node 2, and so on. Okay, so on the top, okay, write 1, 2, 3, 4. Same thing going row wise also, write 1, 2, 3, 4. Okay. Faculty members, make sure I'm only looking at one video here. I'm not seeing all, but I'm assuming all of you are doing it. So on the top, when you wrote 1, 2, 3, 4, 1 corresponds to node number 1, 2 corresponds to node number 2, 3 corresponds to node number 3, and 4 corresponds to node number 4. Same thing row-wise. Okay. Now, in the cell marked 1, 1, it's a table, right? You all know table. I don't need to teach you what a table is. In the cell marked 1, 1 is one, we said that a node by itself, 1, 1, there is no edge. Is there an edge for 1, 1? 1 is just by node by itself, right? There is no edge for it. To have an edge, you need to have 2 nodes. Correct? You agree? Edge connects 2 vertices, right? That is the definition. Right? So what do you do at 1, 1? You put 0 there underneath that. Because the thing is, I did not, just under 1, 1, right? Top one you wrote 1, and row also you wrote 1. There you put a 0. Okay. Now you go to, going row wise. Now you go to 1, 2. Okay. In 1, 2 cell, do you see 1 and 2 vertices connected in the graph? No. So you put another 0. Same thing, go 1, 3. Put another 0. Now you see 1 and 4 connected. What do you put there? 1. Do you see how we got 0, 0, 0, 1 now? Now the girl earlier who I was picking on her, who was putting her hand on chin and she put it down promptly. Now I want that girl to raise her hand if she understands this. Okay. You can raise it comfortably. You don't have to do it quickly. Split second thing, right? You understand it, I'm assuming. You're all smart, okay? Okay. So now I told you how to do it. You can fill the matrix easily. So let me go to the... Okay. Now here is the fun part, right? You did it. Now I want you to draw adjacency matrix for each of these graphs. Okay? Take, I would say take 5 minutes to do that. That's the group, that's the exercise. Okay? I gave you 2 graphs there. I want you to draw the adjacency matrix. And I showed you how to do it. Okay? 5 minutes. Starts now. I'll go on mute while you're doing correct answers, okay? Who put it? 205736546 put it already. JNTUV, you can turn on your video. Same with DNV Shamkumar, Kite Guest. Okay. Wonderful. Now there is a second part to the question, right? Can you show adjacency lists for each of these graphs? Now students, you must be wondering, what is this? Pratap sir did not teach us what adjacency list is, but he's asking us to do the exercise to show an adjacency list for the graph. So who knows what an adjacency list is, right? Now, if you don't know what an adjacency list is, you have faculty coordinators in each of the classrooms. They all know what an adjacency list is. Ask them. Now, if the faculty member conveniently turned off the video and went out to either smoke or get a cup of tea, whatever, right? You ask your peers. There'll be at least one student in every classroom who would know what an adjacency list is. That's the law of nature. Okay. If you don't know it, open up your cell phone and then Google search what an adjacency list is. Or if you see Who Wants to Be a Millionaire or Kaun Banega Crorepati, you can phone in your mom or dad or friend for help. All those things are permissible, okay? But I will move on, okay? You just try to, the intent is I just wanted to throw in a few words there where you can learn on your own some of these things, okay? I think a lot of you put the answers there. That's good. I trust that whatever you put is correct, okay? Let me go to the next slide. I just wanted to introduce you to the sum of subsets problem. Okay. Let me take another example. Give me a second. Let me take an easy example. 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Tell me which numbers would add up to 9. Tell me the subsets. Put it in the chat, okay? Tell me what numbers you add up to make it sum as 9. What are all the subsets that you have to make the total 9? Okay, you have numbers 1 through 9. Pick combinations of numbers whose sum would add up to 9. You can put it in the chat. Okay, 3 and 6. All the subsets. Okay, PVP Siddhartha, you got your chance. Give chance to others now. PVP Siddhartha is on a roll. Give chance to others. PVP. You get it, you get it. Let others do it. Two 5 7 3 6 5 4 6. So easy, right? Sum of subsets. That's what it is. That is the actual meaning of it. I did not have to give a big 30-minute lecture to tell you what sum of subsets is. I just made you do it, and you know what a sum of subsets problem is, right? So let me go to the presentation mode here. Give me a second. My screens are screwed up here. Give me a second. Okay. So what it is, some problem is to find subset of elements that are selected from a given set whose sum adds up to a given number k. Okay, so I gave you an example. Okay, already, so I don't need to show that example. Now, how do you determine all that? If I just gave you that number 1 through 10 and I made you do it, it was relatively easy. But in general, if you have to do an exhaustive search for subset sum, if you have n numbers, the combinations that you have to see, that set which contains all subsets is 2 raised to n. That's a lot of numbers, right? So obviously we can use backtracking algorithm, okay, to allow us to, if you optimize it, it allows us to prune some of the dead ends or unlikely to get the numbers, right? Instead of doing the complete search. So I think I kind of showed you this picture, I vaguely remember, in the last class. One second, somebody is saying something here. Gist, okay, thank you. Okay, I like gist. Okay, good. So here's an example which assumes that the set has 4 elements, right? W1 to W4. Okay. With your mind, take a picture of that thing and it's embedded in your mind, right? Okay. I gave some explanation here, which you will understand anyway when you're doing the tracing of the code. Okay. So in the picture, every node represents a function call and a branch represents the candidate element. Okay. Since there are 4 elements here, you start with the root. Okay. And then all the candidate elements, you can see you have them W1, W2, W3, W4. Okay. Okay. So when you are starting from the root, you are considering every element of the set as a different branch. Because with that number, what is the idea behind it? With that number as a starting point, you will follow the branch depth first to continue to add those numbers to see if it will add up to the number that you are interested in. That's what the definition is, right? Where it says, where was it? See, whose sum adds up to a given number k. So that is the reason why we follow each number depth first and see if that path leads you to that number k. That's what we are doing here. Okay? Keep that in mind. Now when you go to the next level subtree, you are looking at the subset that includes the parent node, because that is the first one number that to add, right? And then whenever you are branching to the next level, you will look at the element at that level to see if it can be added. Right? Let's say you are at, when you add the 1, 2, 3, 4, 5, 6, 7, 8, 9, when you were at 1, then you added 2, you are still within the thing, within the scope of getting to 9, that is 3, right? And then you will add another 3, that is 6, then you add 4, it doesn't work. At some point your algorithm will say, I will not consider any numbers greater than 3, right? Because 6 plus 3 is 9, right? So like that the tree is allowing you to keep track of that. Okay. Now, notice the last but one bullet. We are saying if we are at level 1, meaning you're right at the root. Agree? Right? I'll go back again one more time. Level 1 is that level 1. The way instead of calling level 0, the author here considered the root as the level 1. So that means you're just starting out. All the elements are candidate elements. W1, W2, W3, W4, whatever the values are. Because you're just starting out to come to a given number, right? By the way, all these are supposed to be non-negative numbers. That's another constraint. Okay. Now, if you take level 1, right, W1, okay. Now you are coming to leftmost branch 2, okay. Since you have already considered W1, it's common to say the only other candidate elements are W2, W3, and W4. Do you agree? Anyone has questions? I started at node 1 or level 1. All the 4 elements are for consideration. That's why you have branches W1, W2, W3, W4. Now you have to go to each of the branches, right? Because you want to start adding some. since we already considered W1, what are the other three candidate values that we have to consider? W2, W3, W4. That's why when you go to this node called 2 here, okay, those are not the numbers W1, W2, W3, W4. Those are the just showing you the representation of the bubbles. That's all. So at 2, if you see the branches, you have W2, W3, W4. Now let's take the same approach and go to the leftmost. Now when you take W2, then you come to this node 6, right? So since you already considered the two elements, W1 and W2, the only branches you can have are W3 and W4. You agree? Let me pull it up. Okay. I will do the, let's do 205, 736, the gist. Show of hands. Do you agree how we come to 1, from 1 to 2, 2 to 6, and how the branches are going? I can't see your video clearly, but if you raise your hand all the way to the top, maybe I can see. Okay, what about PVP Siddhartha? Do you understand? Raise your hand. Excellent. PVP Siddhartha is on a roll today. I think they all deserve a nice lunch coupon. Ask your faculty member to give you 50 rupees lunch coupon in the canteen, right? I'm assuming you'll get one dosha at least for that. And I'll reimburse him for that on my behalf. Okay, so that is how you build this tree. Okay, that is one thing. Okay. Now, get some practice, take some numbers, and then you draw those things, you'll get some practice, but the programming example that you will trace shortly will give you that, okay? Okay, let me go. So, what are we doing? As we go down along depth of the tree, we add elements so far. Remember, that's what just initially I said, right? We add elements so far. And if the added sum is satisfying the constraints, we'll continue to generate child nodes further. If you add that 1 through 9, and then I'm looking at to sum 9, right? We added 1, to 1 we added 2, to 2 we added 3, 6. So far we added all of them. The moment we add 4, the second bullet comes into play because the constraint is not met. Correct? Because if I add 4 to the total 6, it will be 10, and I'm looking for 9. Constraint is not met, so I'm going to stop building that branch. Okay? Whoever that madam is, she was doing something very funny there. What was she doing? She was snatching away paper or something. Whatever you're doing, madam, that's good. It's helpful. Maybe the students are drawing some pretty picture of who knows, their girlfriend or boyfriend, whatever. Okay. Okay. No, actually, I have an easy solution. When I was in college, faculty members, pardon me if I'm sharing this story, okay? I went to Jntuk Hyderabad. So when I was in college, when I know that the lecturer was boring, we just used to go and sit in the sports room and play caroms. Okay, we can do something like that here, right? Okay. That's what it is. And what do? You construct to capture the concept. What you're basically doing is you're building a binary tree or state space tree. Okay, you can actually do it as a binary tree. I didn't do it. This is not a binary tree, right? If you go here, obviously this is not a binary tree. Binary means you'll only have 2 branches. Remember we talked about binary trees earlier? And binary trees are very interesting trees, right? A lot of efficiency there in terms of tree traversal and all that, right? And then remember the binary search algorithm that we did? Everything is based on the concept of binary tree. Here I showed a general tree. The best way to do that would be to do it to a binary tree. That's what this is saying. So, okay. Now I'm saying if left and right children represent respectively inclusion or exclusion. Okay. All the theory doesn't make sense. Let me show you the tree. Okay. So, here is an example where I have these numbers called 3, 5, 6, and 7. Okay. And then when you slightly different, right? If you compare it to the previous tree, this is slightly different, right? So you started the root. You are taking 3 to begin with. I'm following the left side of the tree. And you're looking at it, it's left side. So you see the comment there with 3. So you come to the node called 3, right? Because at that point of time, the sum is what the nodes are showing the sum. Okay? Got it? So then with 3, then you add 5 to it because that's the next element, right? You build a full tree, 5, then it becomes 8, then you add 6 to it. Okay? Then it becomes 14. Okay? Now going back there, one level up, if you when you're at the value node which shows 3, without 5 it will still remain 3. So every number that you're considering, you're doing with and without, with and without. Okay, see, slightly different variation of how the tree is constructed, okay? It's a binary tree. So I'll repeat one more time. The way it is, you started at level 0. When you add the value 3, the number 3, you go here. You either add or you don't add. So if you look at the right side of 3, that means that is without 3. So the value still remains 0. Okay. Now going on the left side, after 3, next one was 5. So he says with 5 or without 5. 2 branches. Okay. With 5, if you do it, you will get value 8. Without 5, it is still 3. Now after 5 is considered, then you have 6. So if you look at the without 5, 3 there, you do with 6, without 6. Okay. Now, what is the value? Now, what are we doing once you build a give copies of that to the students, and then let them trace the code. Okay, they are marrying the concept to the practicality of implementing it. That is what we are doing here. Okay. Now, how come nobody is responding when I put it in the chat? Can you hear me? PVP Siddhartha, can you hear me? Raise your hands if you can hear me. Okay, that's good. Now, the esteemed faculty members, since you can hear me, I also put it in the chat. Did you see my chat? If so, can you take the lead and say yes in the chat, so that way others will understand that to type yes if they can hear me? Unless your laptop or something, you should be able to still figure it out. Okay? Ask your peers, ask your faculty members. We are here to help you. Okay? Ready, set, go. Don't stare at the screen. Get your paper, pencil out. I'm assuming that somebody is already printing out the Word document in the classroom. And for sake of convenience, I'll put one piece of code. Let me see if I can put one piece of code here visible to get going, right? It's kind of hard to. Hey guys, hold on 1 second. Sorry guys, I had to take that call. It was my niece calling from India. Just wanted to make sure there is no emergency. There is no emergency. Okay, thank you. Let's see. Then it will be so small that you won't be able to read it. Okay. I'm assuming you are able to print it out and then do it. I will go on mute, but I'm monitoring my chat if you have any questions. Okay? On the videos, I see PVP Siddhartha videos. Who else I see? I don't see video for ABR, DNV, DMS, JNTV, JNT Kakinana. Unless you all vanish from the classroom. PVP Siddhartha faculty member, thank you for facilitating. I appreciate that. Since I see only your video, I can say that. And of course, just also. No, I don't see. Yeah, I can just do that. What are you looking at? You're looking at the screen there, the code, or what are you doing there? Or you're waiting for the faculty members to print out the Word document and give it to you? What exactly are you trying to do there? Watching the code. How are you watching the code? I want you to do it, trace it, right? Watching code doesn't help. Okay, you're watching the code on the screen. Is there a way you can print it out? It's kind of hard to trace it watching the code on the screen. You want to typically when I'm tracing that, I print it out, I make notes on that code also, right? If you have a printer in the classroom, it's easy to print. Unless you had some budget cuts in Andhra and you don't have printer paper or printer ink. Or you feel like you don't want to cut too many trees by printing. So I just wanted you to do it for 10-15 minutes, then I can kind of walk the code with you together as a class. Okay, everyone comes to the classroom with laptops, or we do it with computers. I understand the challenges sometimes in different parts of the world. Level pseudocode in an exam for these problems. That's the reason why I gave you those three structures and all that I walked through. Because to write an algorithm is very easy. To write it in code is a little bit more challenging. Okay, I'll go on mute again for another 10 minutes.